Okay, welcome back to the third video in our thermochemistry series, and we're moving on to describing the changes in heat. So heat transfer processes during chemical reactions or physical transformations. Now, what we're going to be focusing on is the enthalpy. Now, the enthalpy is equal to the heat energy transfer if we are at a constant pressure. So the symbol for enthalpy, I think you've seen this before, is delta H, and we would say that delta H is the heat transfer at constant pressure. So heat's either going to be lost by the system, which it does this in an exothermic, or gained by a system. So it's really important to consider the difference between the system and the system's surroundings. And we'll see this in our next slide coming up. So let's move forward to distinguish and spend a little bit more time on the difference between exothermic and endothermic. Now, we call the process exothermic, because heat is exiting, you can think of it as that, when heat is lost or released by the process. Now, the sign of that energy, delta H, is going to be in joules, and the sign of those joules would be negative for an exothermic. Well, if the system is releasing heat, it's releasing them to the surroundings. That means my surroundings are going to get hotter or increase in temperature as the heat is given off by the system. So the container will feel hot, and you can become part of that surroundings, and your hand would feel that heat. Now, a delta H being negative or exothermic is considered a favorable situation for a process. Now let's look at the other one. We've got a picture of this, a few pictures of this that I think might help you out. So if I have a reaction going on inside of my Erlenmeyer flask here, if it's an exothermic situation, that means that heat energy is being transferred from the reaction to the surroundings. And the surroundings would be my Erlenmeyer. The surroundings could be your hand, or whatever is not the point at which bonds are being broken and bonds are being formed. Now, since heat energy goes from high temperature to low temperature, it's going to cause the temperature of the surroundings to increase. So it's heat transferred from the surroundings into the system. The temperature of the surroundings increases. So if the surroundings get hot, we know that's an exothermic reaction. And in this point, the energy releases heat as more bonds are formed than are broken. A hot pack would be a common example of this. You break this open, the chemicals react. It's an exothermic process. That heat is then released to your shoulder or your neck or wherever it is, your knee, wherever you need that that heat to help you feel better. That's what a hot pack is. Now let's contrast that to an endothermic process. You can think of endothermic as an entering. Heat is entering, so it's endothermic. We would get a positive value for our joules because heat is gained or absorbed by the system. So we'd have a positive enthalpy, assuming we're at constant pressure. We can equate heat and enthalpy. Now, the heat's got to come from somewhere, and that heat is pulled in from the surroundings. So the surroundings get colder. The temperature decreases. In our case, the container will feel cold, and I hope to do a demo that will show you a really nice endothermic reaction. So let's see that in a more visual picture format. So We've got an this is endothermic, sorry, that's a typo, our endothermic process. Okay, in an endothermic process, the Q is going from the surroundings, the heat is going from the surroundings into our system. So if our surroundings are losing heat, their temperature is going to decrease. So we take the heat transfer processes from surroundings into the system. Heat is lost by the surroundings, so the temperature of the surroundings decreases. Okay? The energy required to break bonds is greater, so the energy for breaking is greater than the energy that's going to be released when bonds are formed. Now, cold packs would be an example of this. You break them open. The cold pack reaction absorbs heat from the surroundings. So your surroundings temperature decreases, and that's why your neck or your shoulder or whatever, your knee, whatever injury you have would be cooled off by these as the system draws heat from the surroundings, in that case your body. Now, let's summarize what we have for that. Sorry about that typo in this slide. Let's summarize what we're working on here. For endothermic, we've got a variety of ways that we can communicate these different processes. Verbally, for endothermic, we would say that energy is required. For exothermic, we would say that energy is released in the process. In terms of an observation, for endothermic, the temperature of my surroundings would decrease. For an exothermic, the temperature of my surroundings would increase. Now, in terms of symbolically, we would have delta H being a positive value, some positive kilojoules or joules. For exothermic, delta H would be some negative value of kilojoules or joules. In a reaction, we would write the heat term as a reactant. So heat plus A plus B going to some product C. So heat's written as a reactant. We never subtract in a chemical reaction. It's always going to be either plus on the reactant side, or in the case of endothermic, A plus B going to C plus D. We would put heat as a product. Again, we only add in chemical reactions. So for exothermic, it's a product. For endothermic, it's on the reactant side. Now, graphically, let me pick that up on the next video so that this one doesn't go too long. So I'll see you in just a minute to show you how we would do this graphically.